is Édouard Brezin. He could not come, but he was very kind to accept to deliver his lecture by Skype. So, Édouard, the floor is yours at a distance.
Thank you, Mark. Thank you. I hope you can hear me. I want to apologize for a number of reasons. First of all, Robert Brout was someone I liked very much. At the time, scaling laws, universality, renormalization group was being founded. I had many encounters and discussion. Robert very often didn't believe part of the theory, and it's very healthy. This is part of science. The second apology is that if I look at the program, I wish I could attend. I mean, the lectures look really interesting. And then I'm sorry not to be present, and I understand how painful it is to listen to someone away. So let me try. This is what I would like to cover. In other words, I will cover a subject which is all well known for a number of times. The reason for going into this very well-known part of the theory is that this conference is a mixture of high-energy physicists and statistical physics, and I thought that maybe it's interesting to see the perspective of statistical physics, because the problem of spontaneous symmetry breaking and phase transition has been with us for many, many decades. So let me start with energy and entropy. And sorry for going back to the basis, to the elementary. I think one should realize that the competition between order and disorder is present in the very principle that Boltzmann and Gibbs put forward for statistical physics. Let me remind you of how this competition arises in statistical physics. As you know, the partition function, the physics, which is the log of the partition function, is given by the sum over all the microscopic configuration of exponential minus beta times the energy. Well, the number of configuration is typically very, very large. For instance, if you take the simplest n Ising spins plus or minus 1 variables, the number of configuration is exactly 2 to the power n. However, the number of distinct value of the energy is very small. The ground state is when all spins are parallel, and then you can get excited state by flipping a few spins, and therefore you can replace the initial sum on configuration by sum over energies, distinct energies, which are much less. Therefore, each distinct energy has a typical huge degeneracy W of E. So the initial sum can be written as sum on energies. If you do that, you remember that Boltzmann identified the energy with W, or rather its log, to make it extensive, proportional to the number of particles. Therefore, if you replace W by the exponential of S, you end up with this formula in which the sum on energy is exponential minus beta times the familiar combination E minus Ts, which is called the free energy. E and S of E are extensive, proportional to the number of particles, and therefore this sum is dominated by the minimal value of E minus Ts, because the factor is huge, which is n, the number of particles. So how do we minimize E minus Ts? Well, for T small, E minus Ts is given by energy. So for T small, this favors low energy states. For T larger, the factor Ts is more and more important. And finally, the entropy wins, and higher energies are allowed, provided their entropy is large enough. So this is the scenario of the competition between order and disorder that Boltzmann and Gibbs have left with us. However, for many decades, I would say until the years 40s or so of last century, the debate on phase transitions described by Bowman Gibbs was very intense. Some people believe that the only thing one could do is make a theory for one of the phases. For instance, take a liquid gas phase transition. For the gas, one can make a simple expansion in powers of the density called the Fourier expansion. For liquids, there are various approximations, which goes with many people, such as Ornstein-Zernike. The phase equilibrium is obtained simply by equating the two series. However, there was doubt for many years whether a single unit theory could encompass a liquid-gas coexistence. And this question was solved, to my mind, only for the first time by Rudolf Peierls. So let me go to what Peierls has done. Peierls 1936. 1936, Peierls deals with the Ising model on a plane, 2D. This is 8 years before Onsager solved the 2D Ising model. So he simply deals with the model without its solution. However, what he derived is that at temperature low enough in this 2D model, there is a spontaneous magnetization. Let's review what Peierls did. So the energy for this Ising spin, plus or minus one variable, is given, as you know, as a sum on the lattice of nearest neighbors, energy minus J times nearest neighbors, and then eventually some external magnetic field. If you consider the magnetization, which is the average of the spins divided by the number of spins, and if you take the limit in which the external field goes to 0, you find 0. The result from Z2 symmetry is 0 for obvious reason. Therefore, in some sense, you could say there is never any magnetization. And one could say that it's true, that the fact that there is a spontaneous magnetization is an illusion because we are unable to deal with finite system. But let's go further. So what did Peierls do? Peierls say, well, in practice, you never see anything connected with a finite system. So what happens if, instead of letting immediately the field go to 0, you take the infinite volume limit, the infinite number of particles? So we first let n go to infinity, and then h to go to 0. And Peierls proved that for t small enough, this spontaneization is non-zero. So to my mind, or to my views, this is the first time that a spontaneous symmetry breaking was derived. There are many rigorous derivations. Peierls was a very rigorous derivation, but it has been, of course, over the years, the technology of mathematical physics increased. For instance, Gini gave a beautiful theory in '69. But let's stay with a heuristic argument to understand what Peierls did. Peierls said, let's put boundary conditions in which on the boundary you spin it up. It's equivalent to an infinitesimal external field because it means simply that you have a field on the boundary, meaning that it's a field proportional to square root of the number of the spin rather than the number of spin itself. So it's very small. And then he said, what would be the cost in energy and in entropy in making such a bubble of down spins? So what happens if you make a bubble of down spins? Outside of the bubble, on the periphery, nothing. Spins are still parallel. Inside of the bubble, it's still the same because the energy is the same if two spins are up or if two spins are down. The only energy cost is across the boundary, in which before you put the bubble, the energy is minus J, and now it's plus J across the bubble. So there will be an energy cost which is proportional to the length of the interface, in general for arbitrary dimension L to the d minus 1. So this is the energy, L. Now, what's the entropy? The entropy is how many ways can you do such a bubble? Well, you count. Let's do a bubble by a kind of random walk. We are on a lattice. Each side has about C neighbors. So the first step, I will construct the bubble stepwise. C possibility the first time, C possibility the second step, etc. So the number of random walk is typically proportional to C to the L, multiplied by the number of origin, which is N if you want. But the entropy is the log, and the important part is the log of C to the L. The log of C to the L is proportional to L, so the free energy cost is JL minus TL, and you see there very clearly that for T small, it's the energy which wins, meaning ordered state, and for T larger, at some temperature, which in the unit I've chosen would be J, we know that the system will be disordered. So for T small, the cost of creating the system remains ordered. The true derivation requires multiple bubbles and bubbles inside bubbles, and this is what mathematical physics has done, and Piles also did that. But this is historically the first time that I think spontaneous symmetry breaking appeared in statistical physics. Let's examine what would happen if instead of a Z2 symmetry, we had some continuous symmetry. The simplest example one can think of, but there are many, would be to consider n component. I would still call them classical spin. It would be more exact to call them random vectors of unit length. So again, I have energy, we have an energy which is minus J times the sum over nearest neighbors of the scalar product of two spins minus 1. And each spin has lengths sum 1 to n of sigma I square equal 1. Sorry, I shouldn't call it I. It's a component square equal 1. So the model is invariant now under the group ON. What would happen if we try with such a model to repeat the heuristic argument of Piles? So let's freeze again on the boundary of the sample, the spins. Let's imagine that they all point to the North Pole. If they all point to the North Pole, sigma I, sigma j is 1, the energy vanishes in my unit. So at 0 temperature, the energy is minimum, not simply at the North Pole, but when all the spin point in that direction. So if instead of making a bubble, I decide that on the outside of a bubble, I have spins which go to the North Pole, and inside the bubble, the spins will correspond to a different ground state, a bubble in which the spins point in the direction given by some angle theta, cosine theta, sine theta, 0. Let's see what would be the cost. The entropy estimate is unchanged. It still created a bubble. But let's look at the cost in energy. For the Ising model, the energy that we computed relied on the interfacial energy between two ground states. The minimum energy between up and down was realized by a single plane interface, and the interfacial energy was proportional to L to the d minus 1. Is that the minimum energy for such a bubble? Well, of course not. For the vector model, a wall at which the full rotation theta would occur would cost an energy J1 minus cosine theta multiplied by L to the d minus 1, the number of spin in the wall. But instead of making a wall, we can reach a much lower energy if instead of rotating by theta in one step, you decide to rotate by theta over L in L successive states. Indeed, let's see how much energy that costs. For two nearby spins, the rotation costs J times 1 minus cosine theta over L. For two nearby planes with L to the d minus side, the cost is multiplied by L to the d minus 1. And we have to repeat that L times to obtain the total rotation. So what does that give? That gives J, this is, the first term is the rotation of nearby spin, the second one is one plane, and the last one is the number of planes. And for L large, you get L to the d minus 2 instead of the L to the d minus 1 of the Ising model. The entropy estimate being the same as for the Ising spin, we find that for d greater than 2, for d equal to delta F, the delta of the free energy, is negative for any positive t, because the delta E vanishes, or is a constant. However, for d greater than 2, for t small enough, there is an ordered state. Therefore, contrary of the Ising model, we required dimension greater than 2 rather than greater than 1 to have a phase transition. This is hand-waving. However, the derivation, the rigorous derivation of that, followed in statistical mechanics by Mermin-Wagner's inequality, which proved that in 2 dimensions one could not have long-range order, phase transition, and later in field theory, as we all know, Coleman proved that in 2 dimensions, the fact that one cannot have two-dimensional Goldstone-Moson, there could not be any broken symmetry. So that was the next story, and let me conclude that part with an important remark. The absence of spontaneous symmetry breaking for a continuous symmetry in 2 dimensions, which we just show the argument, does not forbid the existence of a phase transition without order parameter. I must say that was a great surprise when Kosterlitz and Saarles proved in 1972 that in the celebrated XY model, a model with O2 symmetry, that the model had a phase transition, a high temperature phase with exponential fall-off of correlation, and a polynomial fall-off below Tc. It has no proper order parameter. This is forbidden, as we saw, both by Mermin-Wagner and Coleman. It is a phase transition, of course. It's a phase transition of infinite order, meaning that the free energy at the transition point is not only continuous, but all its derivatives are continuous. It is one of the things with analytic function, which can have essential singularity, which is the case, and have 2 different analytic functions on both sides. And the transition, as Kosterlitz and Saarles proved beautifully, is induced by something which is more topological, which is the unbinding of vortex-anti-vortex pair. So that's the early history of phase transition. Still, some puzzles were left with this. Let me mention 2 puzzles. We have argued that there was a non-commutativity between the thermodynamic limit and a vanishing external source or a symmetry breaking boundary condition. However, there are cases in which there are no such physical symmetry source. For instance, superconductivity. As you know, superconductivity, the order parameters is pairs of electrons of opposite spin, and you cannot simply add to a system a pair of opposite spins electrons. The same is true for the superfluidity of helium, for instance. The order parameter is the condensate, which is the creation or annihilation operator of a helium atom with zero momentum, psi tilde of 0. So they are not such physical source. So can we replace the infinitesimal source by another argument? The second puzzle, I will come back to it. The second puzzle is that there are phase transitions, such as a liquid-gas transition, in which you don't see any symmetry between the liquid and the gas. So why is this spontaneous symmetry breaking? Is it relevant to the liquid-gas phase transition? So let's review briefly these two questions. First one, can we avoid the presence of a symmetry breaking source? Well, if I can go, doesn't seem to move anymore. Why is that blocked? Yes, there is an alternative characterization of spontaneous symmetry breaking available even if there is no symmetry breaking, which is long-range order. Let's see what happens, for instance, in the Ising model. As we saw, there was first Peierls definition, large n limit, zero field, you get M spontaneous 1, I will call it. Another alternative definition is as follows. We don't put any symmetry breaking, no symmetry breaking boundary condition, and we consider the expectation value of a spin at x and a spin at 0. And we take the thermodynamic limit, and then we move the 2 points far apart. Well, there is an ordered state. This limit is non-zero, and this limit is the square of the previous magnetization. M spontaneous 2 square, M spontaneous 2 is the same as M spontaneous 1. This was proved, to my knowledge, by Robert Griffiths for the first time, and it shows that indeed one can understand phase transition without symmetry breaking, which was an important step, of course. What about absence of symmetry? There are a number of phase transitions without symmetry, like liquid gas, binary mixtures, and so on, for which there is no a priori symmetry. Can we understand why spontaneous symmetry breaking was relevant? I think the relevance started with the famous celebrated Landau theory of phase transition. Formulated by Landau in 1937, it was based on the concept of order parameter, some number or some set of numbers, which can characterize the physical nature of the phases. Magnetization for magnets, difference of density between the gas and the liquid. Landau theory is not statistical mechanics. It's a pure thermodynamic theory. You don't start with a microscopic energy. Landau said, well, the free energy has to be an analytic function of the order parameter, and it has to respect the symmetry of the problem. Apart from that, if the order parameter is a simple scalar, like magnetization of Ising spin of rho g minus rho l, the free energy per unit volume is some expansion in powers of this order parameter phi. So that's Landau's assumption. It's a very powerful assumption. The quantitative consequences of Landau's theory are simple and numerous. You can derive the property, and you can show easily that it depends simply on the first non-zero, coefficient. All you have to do is know the first non-zero coefficient. For instance, if you have a Z2 symmetric situation, such as magnet, you have only a phi square, phi 4 combination. Fluids, a priori, You could also say it's the lowest coefficient, phi, phi squared, phi cubed, phi fourths. But when you have a polynomial of order 4, you can eliminate the degree 3 by a shift on phi, and the degree 1 by choosing the coexistent line on which the chemical potential of two phases are equal. So the evenness is, in some sense, an asymptotic accidental symmetry. There was no symmetry, but as the phase transition says lambda, everything happened as if there was a symmetry. Of course, the true explanation waited for Wilson's renormalization group, which showed that the highest power was of phi. The Z2 symmetry for fluid is only effective, emergent, as a result of approaching the critical point. Now you could say that correction to scaling, higher powers of phi, could show the effect of odd powers of phi, but the effect is small. If you have a magnet, phi 4, or a fluid, phi 4 is the leading irrelevant operators. Odd powers of phi, such as phi to the fifth, are allowed for fluids, not for Z2 symmetric magnets. However, they are very difficult to test experimentally. You have first a leading irrelevant operator phi 4, seeing beyond it the next to leading irrelevant phi 5 is very difficult, and this was analyzed by Michael Fisher and co-workers a number of years ago. Very difficult. Presumably it's there, but it's difficult to see. So this is an example of effective symmetry and why spontaneous symmetry breaking appears even in some problem in which there is no symmetry. Let me move a little bit further in time and go to Landau-Ginzburg's theory of the Meissner effect. In 1950, Landau and Ginzburg extended Landau's theory, which we just reviewed, to a superconductor in a magnetic field. As you know, a superconductor is characterized by the Meissner effect, which is that if you have a magnetic field, the lines of magnetic field are essentially expelled from the superconductor. The magnetic field penetrates in the superconductor with a very tiny microscopic length, which is called the penetration length. Landau and Ginzburg postulated in 1950 the existence of a charge order parameter phi with mass m star and charge e star of unknown, unspecified nature. One should realize that in 1950, this is pre-Cooper pairs. I mean, as you know, Leon Cooper first argued that if there is pairing at Fermi surface, something has to happen, and this is what Bardeen Cooper Schrieffer showed, and this is 1956. And okay, so let's review Landau-Ginzburg. They say, in the absence of external field, the order parameter has a free energy, which is like Landau, what we just reviewed. There's a phi squared plus b phi 4, and if phi is slowly varying, there is a term which is proportional to gradient phi squared. If A vanishes and changes sign at some temperature Tc, whereas in the famous situation of a second order phase transition with a U1 symmetry, a phase reparametrization of phi, with a superconducting density, you simply minimize F with respect to phi, and you find the superconducting density phi squared, which is minus A is negative, over 2B. So the standard in the absence of phase transition in the absence of a field. Now they say if there is a magnetic field, as we know, the gradient is replaced by gradient minus EA, and there's a magnetic energy which is B squared, rotation of A squared. Now you can minimize, if you minimize with respect to phi, you minimize respect to A, you find this famous equation, which is called Longden Equation, postulated by Longden even before, but which showed that, of course, the magnetic field can penetrate in the sample, in the superconductor, but only infinitesimally with the penetration length 1 over lambda squared. They get by dimensional analysis, the mu e square over m square rho star is just the inverse of a length square. And of course, it is a surprise, certainly not a criticism, but I always felt that Engler and Brout, who knew superconductivity, were inspired by this Landau-Ginzburg theory of the Meissner effect. Peter Higgs, I don't know, he was more entirely a particle physicist. So I don't know, but I think this was a very remarkable achievement of these two people. So it's only after BCS that the microscopic understanding of the order parameter as pairs of electrons of opposite spin, and therefore E star equal to E, was achieved. Let's move very briefly to the renormalization group era. Landau's theory was, in general, qualitatively correct. It was very rapidly understood that its statistical mechanics equivalent, let's remember that there was no statistical mechanics for Landau, it was purely thermodynamical. In statistical mechanics, it's called mean field theory. During the 60s, it was a decade where systematic deviation from Landau theory were discovered, with the intriguing concept of scaling and universality. Universality was really amazing. If you take liquid-gas phase transition, there are hundreds of molecules which exhibit liquid gas and magnets and binary mixture of fluids. They all have the same critical exponent, the same scaling function. We only saw in 1971 by Ken Wilson, whose concept of renormalization group provided a luminous explanation of those concepts, which he was rightly awarded the Nobel Prize in 1982. As you know, Wilson was a particle physicist. He was a former student of Gell-Mann, and his views, his way, his reason for looking at phase transition came from the fact that he was looking at renormalization theory with a viewpoint which was opposite to most people at the time. When renormalization of you could take spacing or infinite cutoff in momenta was regarded by many as an evidence that a theory like QED could be valid from astronomical scale down to the smallest microscopic scale. Wilson had a different viewpoint. He said at low distance, at energy much beyond what can be explored with accelerators, we have no idea what goes on, apart maybe from symmetry. And therefore, he started with the idea that there is an unknown theory at small distance, and he showed that renormalizability is an emerging feature. It's a feature which comes from the fact that at higher energies, at long distance compared to the microscopic distance, a non-microscopic distance, there are emerging features such as renormalizability and symmetry. And you all know that this figure, I don't know if you can see my figure, but it's so well known that in which you have a critical surface with irrelevant variable on the critical surface which lead to the fixed point, and relevant variable which point out, explain beautifully that various models were shown to fall in the same universality class. Numerous techniques such as epsilon, 1 over n expansion, Monte Carlo renormalization group, numerical were developed. And I think it's not the place to talk about it, because this is not the subject of spontaneous symmetry breaking. And let me mention that the recent period is marked by the use of conformal symmetry, not simply dilatation symmetry, which is Wilson's picture, but the conformal symmetry has been recently exploited in any dimension that give spectacular results for critical exponent, which maybe someone will review at this conference, but is really the main progress, I would say, of the last year, Rishkov et al. It's really beautiful. So I will leave this subject here, and I will go to disordered system in the few minutes left. Disordered systems are more complicated, and they have left us with difficult problems which are not yet completely understood. The first one of the first one, there are many, is what I would call the random field Ising model. The random field Ising model is as follows. You take an Ising model, the first term is sum of the nearest neighbors, as before, and then you have a microscopic field which varies from site to site. And the microscopic field H is random. At each site, there is a probability distribution for H, which is even. So physical observable are obtained by a double averaging. The first one is, as usual, in order to get the expectation value, you average over all configuration with a Boltzmann weight. But still, the physics is given by averaging. Once you have done the first averaging, you have to average over the random field to obtain the physical O. And that's very difficult, because you cannot replace this double averaging with an effective Hamiltonian in which you would perform only one single averaging, unless you introduce things like replicas. So you can ask, in which dimension of space is the Z2 symmetry spontaneously broken? Notice that this model is Z2 symmetric. The sigma into minus sigma and H into minus H, with the probability distribution being even, show that indeed there is a Z2 symmetry. So is Z2 symmetry spontaneously broken, and when? Initially, there is a long history to the problem. Initially, in the early 70s, a perturbative argument to all orders in perturbation theory, plus later a magnificent, beautiful, elegant supersymmetry argument by Parisi-Sourlas, led to the conclusion that the critical property of the random system in dimension D were identical to those of the pure Ising model in dimension D-2. So you want, for the random field, to know what are the critical exponent in 4 dimensions. Well, you take the Ising model solution in 2 dimensions, and that's it. So that was a beautiful argument, but very soon, Imri and Ma came with a problem. They say, well, we don't believe that there is an ordered phase below in 2 dimensions. One has to be above 2 dimensions, in particular 3. Their argument was also a bubble argument, which, like the one I sketched earlier, the bubble argument is as follows. You will have, as before, energy entropy, but there is an additional energy due to the random field. If you flip the spin within the bubble, the random field energy is typically on the average 0, but it has an expectation, it has a standard deviation which goes like the square root of the number of sides, L to the D over 2. And Imri and Ma argued that this would mean that for D greater than 2 only, there should be a phase transition. So there was a problem with dimensional reduction, in spite of the beauty of the argument. Still, there was debate for many years, until finally the mathematical physicists, Imri first and then Brinkman and Kupianin, supported by a rigorous construction, the simplest droplet evaluation. They proved that there was a phase transition in dimension 3, whereas there is no phase transition in the Ising model in dimension 1. So the dimensional reduction is lost somewhere below 6 dimension, because nobody doubts that it's valid in 6 dimension. And somewhere it seems to break down around 5 dimension, but the exact mechanism is still debated, still unknown, and I cannot really tell you where the supersymmetry breaks down. Big subject, still debated. The last symmetry breaking, the last minute I have, is on spin glasses. The simplest model of disordered magnet with competing interaction leading to many metastable states is given by a spin system on a lattice with random coupling Gij, attractive or repulsive, with equal probability. Again, there is a Z2 symmetry, as you see, but the system is clearly disordered. The averaging over the randomness is delicate. Averaging the free energy log Z. So you first have to calculate Z, and then, which is difficult, and then average its logarithm. One way is introduced by Edwards and Anderson to do that is to introduce replicas, n copy of the stem system in which log Z appears as Z to the n minus 1 divided by n in the n equals 0 limit. What is Z to the n? Well, Z to the n is sum over n times over exponential minus beta e. So you introduce n replica, sigma I is the side, alpha goes from 1 to n, and then you can perform the averaging. The simplest model, the mean field model of Sherrington-Kirkpatrick, is the limit of infinite dimension in which each pair of spins on this lattice have equally distributed random interaction. There's no distance. They are all nearby. So the model has a global Z2 invariance and, of course, a permutation symmetry, Sn, between the replica. However, what Sherrington and Kirkpatrick discovered in their initial paper, and left to everybody as a puzzle, is that if you take an Sn symmetric solution and solve the model, which is not difficult, the solution breaks down below some temperature, because below temperature, the Sn solution gives a negative entropy, which of course entropy is counting, so it cannot happen. So various unsuccessful schemes of replica symmetry breaking were introduced until Parisi came with a solution in 1979. After averaging, so I will briefly tell you, because I have not much time left, briefly tell you about Parisi's solution. So you introduce what's called the Édouard-Anderson parameters, which is you take two copies, two replicas, and you look at their overlap. Are they similar or not similar? Now, if there were essentially Q alpha beta would be the same for all alpha betas except maybe alpha equal beta. But Parisi does the following. He takes the n replicas and he divides them into n over m groups of replica. If two replicas are in the same group, this takes Q1. If there are different groups, this is Q0. First step. Then, says Parisi, repeat that. Divide M into M over M prime groups of M prime replicas, for same subgroup Q2, different subgroup Q1. And you do that ad infinitum until finally you end up with something which is called an ultramatrix tree of states. You continue to real M's, which normally are integer between 0 and 1, and take the n equals 0 limit, and then, says Parisi, you minimize the free energy with respect to Q of x, and this was Parisi's solution for the free. as you can imagine, the fact that you have an infinite breaking of Sn symmetry with n goes to 0 raised a number of skepticism. However, again, mathematical physicists advance, and in the school of Guerra in Rome, Talleyrand at Paris University, they finally managed to prove, not using replica, that Parisi's solution was exact for an infinite number of dimensions for the Sherrington-Kirkpatrick spin glass. So this is infinite dimension. You could say, is Parisi's solution with this infinite spontaneous symmetry breaking, is it valid in the experimentally relevant dimension at 3? It's still debated. There's still vivid conflict. I think at the moment there is agreement that Parisi's scheme is valid for dimension above 6. In dimensions such as 3, there are antagonistic views, and I don't think that one can conclude that it's true in dimension 3. In spite of that, I think that Parisi's mechanism is very important, because after Parisi's solution for spin glasses, the same scheme has been applied to many algorithms in which there is no polynomial algorithm system, which are called complex, in which you cannot find something, the problem which are called by in informatics theory NP complete. So Parisi's solution seems to be the only approach available today to algorithmic complexity. So even if it doesn't apply to copper and manganese in dimension 3, I think its importance for understanding a lot of contemporary problem of algorithmic complexity is essential. I will stop there. I think this was a survey of how symmetry breaking appears in statistical physics. I would like to thank you, and goodbye to whoever is still listening. But I can see the room in the screen, in the corner of my screen, and many friends are still there. Thank you.
Thank you very much for this beautiful survey. Maybe we can take one question. Yes?
Yeah, I have a
short question.
Yes,
Maybe you should take the microphone.
Yes, I would like to hear your comment about if the symmetry breaking invented in condensed introduced by Ising, will it be invented then in particle physics? That's my question. Thank you very much.
Well,
so did you hear the question?
Yes. Is it a similarity between formalisms, or is it identical? Of course, there are many questions of particle physics, such as gauge symmetry, with little relevance in statistical physics, or exotic relevance, I would say. However, the similarity, I would return to Wilson's viewpoint. After Wilson's views on what phenomenalizable theory would be, he turned to critical phenomena because his colleague at Cornell at the time, like Michael Fisher, Ben Woodham, told him, but your ideas should find application in another system in which we are taking a long limit with respect to microscopic, which is statistical physics. So I think that it's not an accident, if I follow Wilson, it's not an accident that the two approaches have exactly similar viewpoints. Did I answer your question?
Yeah, I think, thank you, and I think we should move on and go to the next speaker. So Édouard, thank you very much again for this nice presentation, for waking up early.